Ammonites is an imagined exoplanet conceived to test how diverse chemistry and dynamics could produce unfamiliar planetary environments and ecosystems. This presentation summarizes observed characteristics in high-definition renders, outlines plausible environments, and explores hypothetical life and formation scenarios. All descriptions are framed as informed speculation grounded in planetary science principles, not empirical discovery from probes or telescopes. The name Ammonites references spiral shell morphology seen in some surface and atmospheric patterns, offering a visual shorthand for complex dynamics. Over the next minutes, clarity will come from staged visuals, full disk renders, labeled cross-sections, and simulated flyovers of representative regions. Begin with a visual characterization, color palette, banding, and global features that distinguish ammonites from terrestrial analogs. Visually, Ammonites displays broad latitudinal bands of teal and amber with brighter polar caps and dark equatorial belts, indicating compositional variation. The atmosphere is hypothesized to be dense and nitrogen-rich, with significant volatile components, including methane and exotic halogens that tint clouds. Cloud formations often organized into logarithmic spirals around strong cyclonic centers, producing the characteristic ammonite-like motifs observable from orbit. Spectral models predict reflective aerosols in upper layers, generating iridescent glints at certain incident angles and seasonal shifts in hue. Atmospheric dynamics favor strong zonal jets, with wind shear between bands driving mixing and intermittent convective upwellings seen as bright storms. Surface pressure estimates range from 1 to several bars depending on altitude, supporting liquid phases of volatile compounds unfamiliar to Earth standards. The surface mosaic includes reflective basins, silica-rich plateaus, and extensive organic-rich deltas that suggest active chemical cycling. Liquid bodies contain dense solvent mixtures, possibly hydrocarbon ammonia eutectics, forming viscous seas with low surface waves but complex chemistry. Thermal imaging suggests geothermal hotspots along faulted ridges, supplying energy gradients that could sustain localized chemical ecosystems. Surface minerals include hydrated silicates, ammonium salts, and iron phosphate deposits that form layered sedimentary structures over geologic time. Seasonal tilt drives migration of volatile cycles, causing transient ice veneers and episodic spring floods in low-lying basins. Topographic diversity creates distinct ecological niches, from sunlit plateau fields to deep, pressurized trenches cut by ancient flows. If life emerged, it likely exploits chemical energy rather than sunlight in many regions, with chemosynthetic communities near geothermal vents. Benthic mats composed of polymeric molecules could stabilize sediments and mediate redox reactions, appearing as dark, textured carpets in shallow seas. Floating pelagic organisms might use buoyant gas bladders and photonic skins to harvest diffuse starlight and chemical gradients higher in the atmosphere. Silicate-based filterers or silica corals could build reef-like structures in mineral-rich shallows, altering fluid flow and sediment deposition. Metabolic strategies would likely favor solvent-tolerant biochemistry, robust membranes, and catalytic mineral surfaces, acting as proto-enzymes. Ecological networks could be modular, with localized food webs anchored to energy hotspots rather than continuous photosynthetic chains. One formation hypothesis posits Ammonites as a primary planet in a volatile-rich protoplanetary disk, accreting abundant nitrogen and organics. An alternative suggests a late heavy bombardment delivered ammonia and organics via icy planetesimals, reshaping surface chemistry and volatile inventories. A speculative third model imagines partial differentiation with subsurface oceans insulated by thick crust, enabling long-term chemical stability for lifelike processes. Exploration would prioritize orbital spectroscopy, radar mapping, and targeted landers to sample surface organics and measure atmospheric composition directly. Robotic probes adapted to corrosive solvents and high pressures would test for metabolic signatures, isotopic fractionation, and mineral biosignature associations. In summary, Ammonites serves as a thought experiment, a platform to evaluate how alternative chemistries and dynamics influence planetary habitability. If you enjoyed this video, don't forget to like, share, and follow Mind Beyond Time for more short stories about science, mystery, and the universe.